Hello. We will now discuss Chapter 2, Section 1, which deals with describing location in a distribution. And in the last chapter, we discussed basic descriptive statistics, and we found basic statistics such as measures of center, like the mean and median, and measures of spread, like the standard deviation, the interquartile range, and the range. And but there's a lot of other interesting statistics for us, even though those are sort of our main ones. One of the main which is a location in the distribution. For instance, like let's say for instance you take some test and you make an 84 on the test. One of the things that might be interesting for you to know is how did everybody else do? For instance, it was 84, was that maybe the highest grade on the test, or maybe it was the lowest grade on the test, or maybe it was at, let's say, the 90th percentile of the other scores. And that 90th percentile, what that means, and it's one of our main measures of location, it means that 90% of values were below it. You did better than 90% of people, in essence. And so that's one of our main measures of location, is percentile. We also have what we call a z-score, which is the number of standard deviations. My score is from the average or from the mean. And so showing you those two things are the main two things that we're going to talk about right now in location. I'm also going to talk about transformations of distributions, which is an important concept. And then the last thing in this video I'm going to show you is how to make a relative cumulative frequency plot, which is a plot that can be used to estimate percentiles. But so first of all, let's look at number one here. And it says our context is that the number of computer sales that a worker at a computer company over 9 weeks is shown below. Find and interpret in context the percentile of 14. So we've got 9 weeks here. This is the number of computers that this worker has sold in those 9 weeks, which are nicely put in order for us. And if they weren't in order, you'd need to put them in order to get the percentile. But so there's 14. The percentile is the percent of the data that is below our value. Well, we've got a total of 1, 2, 3, 4, 5. There is 5 values out of, and the total number is 9, and so that would be equal to 5 divided by 9 is 0.5 repeating. So it is the 55.5 repeating percentile. That is its percentile. 14 is larger than 55.5 repeating of the values, and so that is how you find percentile. It's just the percent that are below it. And so and it says to interpret it, so that's finding it. And so interpreting it, it just says interpreting its meaning, it means 55.5% repeating percent of the number of computer sales are below our value, below 14. So that is interpreting the meaning of a percentile. All right, so our other main measurement of location in regards to a distribution is what we call a z-score. A z-score is just the number of standard deviations that our value is from the mean. Let me remind you from the last section, what is standard deviation? Standard deviation is the average amount that that the values differ from the mean or differ from the middle. So if we were to find the mean of these numbers, and the mean of these numbers happens to be 12.1 repeating, and if we were to average the average distance between every point in the middle, that is in essence intuitively the standard deviation. So there's our formula for z-score. So z is equal to x. X is just whatever our value is. Mu, that's the Greek letter mu, that is the mean, that is the average of our numbers, and sigma is our standard deviation. Now, a lot of times you'll see the notation here. Sometimes you'll see the mean listed as x bar. So, and we'll get into really later in the year why is it we sometimes call it mu and sometimes we call it x bar, but I'll go ahead and tell you. Mu is if it's a population value, x bar if it's a sample value. And so we'll talk about that later. And standard deviation, sigma, sometimes you'll see that listed as S. S is a sample standard deviation. Sigma is a population standard deviation. But they're sort of the same concept right now for what we need to know. So the z-score for 18, so you would just say 18, that, minus our mean, which when you find the mean, the average of these numbers, the mu, is equal to, as it turns out, 12.1 repeating. You just add those up and divide by 9, the number of numbers. So that would be 12.1 repeating. And then the standard deviation, which I got off my calculator, and if you want to know how to find standard deviation, you can watch the last video we did on section 1.3, but it ends up being that 6.47 approximately, and so that in fact is equal to 0.910182. Plenty of sig figs there, and so we're a little less than 1 standard deviation above the mean. So intuitively, what is a z-score? It is the number. It is the number of standard deviations. It is the number of standard deviations that my value, or x, just the value you're looking at, is from the mean. So it gives us an idea of how big or how small is our number in general. And we'll talk about this in section 2 too, but most of the time, normally, as we'll say, it's really weird to get a value that is 3 standard deviations above or below the mean. As a matter of fact, once you get to 2 standard deviations below the means, above and below the mean, it starts being pretty unusual. But 0.91 is less than 1 standard deviation above the mean. That means it's above average, but it's not way above average. Anyway, and now z-scores can certainly be negative. Matter of fact, roughly half the time they are. In a normal curve, exactly half the time they are, as we're going to talk about in section 2 too. But anyway, all the z-scores we're going to find here, as it turns out, are positive, and I sort of regret that because a lot of times they're negative. But anyway, okay, so Lucy, problem number 4. Lucy gets a 93 in a test. Her z-score relative to the other scores was 2.1. If the mean of the scores was 83, what's the standard deviation of the scores? And so there's a lot of problems that deal with this formula for our z-score. So you've got to memorize that formula. It's not on your formula sheet. And so we'll just say, okay, her z-score was 2.1, and that is equal to x, her x value is 93, and it says the mean, the mu, is 83, so it would be 83, over the standard deviation, which is sigma, like that. And so we'll just do a little algebra here. I'll multiply both sides times sigma to get that out of the denominator, like that. And so that would give me 2.1 times sigma is equal to 93 minus 83 is 10. Divide by 2.1, divide by 2.1, and our sigma, as it turns out, is equal to 4.762. So there we go. Of course, that's a different data set than what was above. But anyway, so there's our sigma. All right, and so yeah, so problems, there's always several problems involving the formula for a z-score on the AP Stats exam. All right, and let's look at this one. Marty got a 79 on a test that had a mean of 72 and a standard deviation of 5. Sally got an 84. She scored higher on her test, but it's a different test that had a different mean and standard deviation. Her mean was 80 and a standard deviation of 7. Who had the better score relatively? All right, and so that means one way we can compare that is to compare their z-scores. So in regards to Marty, well, his z-score is, he got a 79 minus the mean over the standard deviation of 5. And so Marty, as it turns out, had a z-score of 1.4. In other words, a z-score, he was 1.4 standard deviations above the mean. Pretty far above the mean, but not really freakishly so. And then Sally, okay, Sally, her z-score, well, she got an 80, but, I'm sorry, she got an 84. So she got an 84, and then her mean is 80 and standard deviation of 7, and so that would be 4/7, which is 0.57143. And so therefore Marty had the better score relatively, even though his 79 is certainly less than 84, but evidently his was the harder test. So okay, all right. So then, all right. So that's sort of the main thing in regards to location, percentile, and z-score. Now, the second topic I want to talk about in this video is transformations. So what happens when you have a data set? What happens when you have a data set and you multiply it by something? So for instance, if we took this data set, let's say we multiplied every number by 2, or let's say we added 5 to it, or something like that. And so what would happen to the measures of center and spread? And the most common use of this is when we change units, like when we change from yards to, to feet, or when we change from hours to minutes, or from minutes to seconds, or degrees Fahrenheit to degrees Celsius, that sort of thing. And so here's the two rules that you need to know when you do it, when you do a transformations. I'm going to tell you these from the beginning. So how does multiplying or dividing a data set by a value affect its summary stats? In other words, its mean, its median, standard deviation, IQR, etc. All measures of center and spread are multiplied or divided by as well. So if you multiply every data value by 2, let's say, it multiplies every measure of center, meaning the mean and median, and every measure of spread, the standard deviation, IQR, and range, by 2 as well. But if you add or subtract something, it only affects the measures of center. Okay, and so how does adding or subtracting a value to a data set affect its summary stats? Measures of center get added to or subtracted, whichever you did, but the measures of spread are unaffected. Now, to try to explain this, or to try to show it to you before I do the example, let's say this was our data set. Let's say our data set X was just the numbers 1, 2, 3, 4, and 5. So this is this context could be anything. It could be the number of siblings people have, or the number of cars people own, or something like that. Well, let's say we doubled it, 2x. All right, think about what happens, or I'm sorry, if we added 3 to it. So if we said x plus 3, we added 3 to every data point. So now, as opposed to 1, 2, 3, 4, 5, now we added 3 to all of them, 4, 5, 6, 7, 8. What happened to the measure of center? In this case, the mean and the median are both 3 here, but they're both 6 here, so 3 got added to them, okay? But what happened to the measures of spread? Like the range here, biggest minus smallest, 5 minus 1 is 4. Well, the range here, 8 minus 4, yeah, it's still 4. So the range is unaffected when you add something to it, or if you subtract it. Or if you think about, like, let's say the IQR. The IQR Q3 minus Q1 would be 4.5 minus 1.5, so it's 3. And the IQR is 3 here as well. In other words, they're spread out the same. Everything got pushed up. Okay, so the mean and median got pushed up, but they're spread out. They're the same relative to each other. But if you multiply it by something, so if you multiplied every value of x by 2, so I multiply every one of these things by 2. So now it's 2, 4, 6, 8, 10. So now my data, 2x, would be 2, 4, 6, 8, 10. Now, the mean and median, they get multiplied by 2, but so did the measures of spread. We look at the range of this. The range of this is now 8, which is double of what the range is there. And the same thing's true. It's going to be the standard deviation of IQR. So when you multiply something, it gets doubled as well. And by the way, point measurements are also affected by both adding and multiplying, adding, subtracting, multiplying, and dividing. In other words, like the 75th percentile, that sort of thing. But let's look at our example, and hopefully this will be the sort of thing that you've got to understand how to do. So our example of a transformation, Monique measures the heights in feet of her ferns, getting the summary statistics below. So the average height of her ferns were 4.1, the standard deviation's 1.3, and here's the 5-number summary, the min, Q1, the median, Q3, and the max. There's the IQR, and there's the range. So there's our summary stats, okay? All right, but she puts the ferns on a 3-foot high platform and measures how high the tops of the ferns are above the ground in inches. So it was in feet, but now it's in inches. So the effect of changing from feet to inches has the effect of multiplying all these values times 12. And then what is the effect of raising it 3 feet in inches? Well, that's adding 36 to it. Okay, so our transformation here, it goes, we're taking all of these values and we're multiplying them by 12 and adding 36. And according to our rules up here, the measures of center and spread are both going to be affected by 12 times. But the plus 36 only affects measures of center and point estimates. It does not affect measures of spread. By point estimates, I mean things like Q3, Q1, the min, and the max. In other words, really specific values in there. But the key thing to remember, measures of spread are unaffected by adding and subtracting. So in other words, so for this mean, so the way you'd find this mean of, so let's write this down here. So now we're looking, here's x. So there's my summary statistics with x. So now 12x plus 36, okay, what is this going to be? Well, with the mean, it's going to be 12 times 4.1 plus 36, and that in fact is equal to 85.2. Okay, but in regards to the standard deviation, it is not affected by the plus 36. That is a measure spread. So that's just going to be 12 times 1.3, and that in fact is equal to 15.6. Okay, and then the minimum and Q1, these point they're affected by everything. So the min, so that is going to be 12 times 1.8 plus 36, and so that would be 57.6. Similar thing happens to Q1, it ends up being 66. The median is 82.8. Q3 is 104.4, and all these we're multiplying them by 12 and adding 36. The max is 104, so 104.4, but IQR is a measure of spread. I'll circle the measures of spread. They are not affected by the plus 36. They're only affected by times 12. So that times 12 is 38.2. There's a measure of spread. And then another measure of spread, the range, 51.6, is not affected by the plus 36, just the times 12. So that's transformations. All right, and then the last major concept that I want to show you is how to create an ogive. Now, creating an ogive is a bit tedious, and actually doing the whole thing of creating, well, what I call an ogive, it's what we call a relative cumulative frequency plot. That's what they call it now. We used to call it an ogive, but it's what we call a relative cumulative frequency plot. But so it hasn't, creating this full thing, like I'm going to show you, hasn't been on the AP Stats exam, and you say, well, why should I pay attention to this then? Well, there's been a lot of questions on interpreting one of these plots, and to me, in order to interpret it, you got to know how it was created. So, so that's why I'm doing it, and also creating a frequency table and showing the cumulative frequency and the relative frequency. Understanding what those concepts are really important. Really important concepts. So what we're going to do to create a relative cumulative frequency plot, we need a frequency table first. Then we're going to go cumulative, and then we're going to go relative. Let me show you what I mean. So a frequency table, here's our data. So this is the number of points that a basketball player scores in a game. And so we are going to create classes. Okay, we're going to create a frequency table, just like we did when we made an ogive. And you say, well, the numbers are going from 4 to 37. And so what should my class size be? I've got to start at 4. So I'm going to start at 4. And so, 37 minus 4 is 33. We want at least, at least 5 or 6 classes, I would say, with the data of this size. So I'll just make my class size as 5. And so the first class would be 4 to 9. And then the second class would be 9. I keep adding 5, 9 to 14, and then 14 to 19, and so forth. And then we keep going until our classes capture all the data. 19 to 24, 24 to 29, and then 29 to 34, and then 34 to 39. And that would capture all the data, like that. And let me remind you, these things are inclusive on the left side. I mean, think about 4. 4 has to go in this class, otherwise there's no class for it to go in. And so 9 goes in this class, the second class. 14 goes in that, so it always goes in essence in the lower one. So this is, we'll go frequency now. And so it's very nice, these things are put in order, that makes things easier. So how many are between 4 and 9? Not including 9 itself. 1, 2, 3, 4, 5. So we have 5, and I tend to make tally marks because if it's not given to you in order, it's easy to do tally marks. So anyway, and so how many are between 9 and 14? Not including 14. So you would say, well, it's 1, 2, 3, 4, 5. So that's that. So 1, 2, 3, 4, 5. And then how many are between 14 and 19? Not including 19. 1, 2. So 1, 2. How many are between 19 and 24? Not including 24. So that would just be 1. And so that is that. How many are between 24 and 29, not including 29? Well, that would be 1, 2. So that would be 1, 2. How many are between 29 and 34, not including 34. So that would be 1, and then the other two, 34 and 37, would go here. And so that is a frequency table, as we did, and so that is a popular thing in the world of stats. Now, what is cumulative frequency? So now we'll create a cumulative frequency table. So cumulative frequency just means you add them up as you go along. So the cumulative frequency, we start with 5 in the first class, and then to get to the next class, we're adding 5 more, so it's 10. So this is telling me there's 10 values that have occurred at this class or before. That's what cumulative frequency means. Then for the next class, we add 2 more. So it'll be 10 plus 2, and that's 12. For the next class, 12 plus 1 is 13. So that's telling me there's 13 values that have occurred in this class or before. In other words, before 24, since it doesn't include 24. 13 values occur before 24. And then 13 plus 2 is 15, and then that would be 16. There's a total of 18. That is what cumulative frequency is. Now, let's talk about relative. So let's talk about relative cumulative frequency. Relative means create a proportion out of it, or in other words, make a fraction or a percent out of it. A fraction or a percent. Fraction or a percent out of it. And so what that means is well, our total size is 18. There's 18 numbers. So relatively, 5 out of 18 occur in this class, and that in fact is equal to 0.27 repeating. So relative tells me the percent that occur before that. And in essence, relative cumulative, and that is what? It's a percentile in essence. And so then for the next one, you'd say 10 divided by 18, and that in fact is equal to 0.5 repeating. And then 12 divided by 18, and that's 0.6 repeating. 13 divided by 18 is 0.72 repeating. 15 divided by 18 is 0.83 repeating. 16 divided by 18 is 0.8 repeating, and it always ends in 1. So this is in essence the percentile associated with the edge of each class. And so let me show you. And so making a relative cumulative frequency plot is in essence graphing those numbers is what we're going to do. And so what we'll do is, let me just put this graph here, is to make a relative cumulative frequency plot is in essence a plot of percentiles. So your vertical axis is percentile, and so you write the percentiles down, and then your horizontal axis is your whatever it is your data is, the number of points scored in a basketball game. And so what we'll do is let's see if I can get this to where you can see it, is we're going to graph. So I've got all the classes down here, and then I'm gonna plot. What I'm going to plot is on this graph, I'm going to plot the right side values with that, because this is saying that 27.7 repeating percent occur before 9. And so that is in essence what a percent is. So with 14, I'm going to graph it with 0.5 repeating. With 19, I'm going to graph it with 0.6 repeating. And so what we'll do, first of all, we start out with 0. So we start out with 4 in this case. No values occur before 4. The first number is 4. And so the percentile, there's 0% that are below 4. And then at 9, so when you look at 9, it is 0.27 repeating. And so we would go up to that as best we can. We want to draw it as nicely as we can. So it goes up to about there, and I connect the dots. And then with 14, it goes with 0.5 repeating. So 14 goes with 0.5 repeating, and that's about there. So it goes like that. And then I'll just complete these. 19 is 2/3, 0.6 repeating. So 0.6 repeating is about there, and connect those dots. And then 24 is 0.72 repeating, so that goes about there. And then 29 is 0.83 repeating, which goes about there. And then 34 is 0.8 repeating, which goes about there. And then lastly, 39. All the numbers occur before 39. And that is how you make a relative cumulative frequency plot. It is in essence a plot of percentiles. Now, there's a couple of things here that, now, like I said, creating that by hand has never been on the AP Stats exam. What has occurred is they give you this graph. And in order to be able to do these problems, in order to be able to understand it, I think doing it by hand at least one time is an important thing to do. But there's really two things you've got to be able to do with it. You've got to be able to estimate percentiles using just the straight edge. And you've also got to be able to understand the significance of when it's steep and when it's shallow. So anyway, so let me show you this. So in another context, we are given this relative cumulative frequency plot. So we are given this plot, all right? And in this case, the context is the number of apples in each tree, in this group of apple trees. And so, so there's two things we can do. First of all, with this, we can estimate percentile. Like, let's say we wanted to estimate the median, the 50th percentile. You would just go to 50% to the graph, you go over, and then you would go down. And you would say, I'd estimate the percentile to be about, I don't know, maybe, what is that, about 117? So that is what I would estimate the 50th percentile to be. Or you could say one tree had 100 apples. What percentile is it? Well, you go to 100 apples, and so you would go up like that, and then over, oh, that's about maybe, maybe like 12. That's about the 12th percentile. So estimating percentiles is a skill you've got to be able to do with the relative cumulative frequency plot. The other thing is to be able to, what's the significance when it's shallow and when it's steep? And wherever it's shallow, it means there's not many data points there. So there's not many trees that had between 80 and 110 apples. But wherever it's steep, it means there's a lot of data points. Like in our data, in this problem up here, we had a lot of values between 4 and 9 and 9 and 14. And those were the steepest parts of our graph. Where whenever it was flat, it means we didn't have that many data points. Like between 19 and 24, there was only one data point, so it was flat there. So, so let's answer the questions in regards to this ogive, and that'll be it for this video. Find the IQR using the relative cumulative frequency plot above. Remember, the IQR is equal to Q3 minus Q1. We learned that in Chapter 1. And so that, the Q3 is the 75th percentile. 75th percentile is the upper quartile, otherwise it's the 75th percentile. It's bigger than 75% of the values. Minus in Q1 is the 25th percentile. So it is bigger than 25% of the numbers. It's a lower quartile. Well, let's estimate it, and it's kind of sketched on here for us. So 75th percentile, you go to 75% on the y-axis, and you go over and you go down. It's about 120 apples. That's the 75th percentile. Minus the 25th percentile, well, that's about 110 apples. You go over and down 110. So in other words, we estimate the IQR to be 10 apples. So there we go. So that's how you do that. What percentile is 124 apples? So now we're going the other way. Now we're going to go, as opposed to going over and down, now we're going up and over. So 124, that's about right there. And so we get up to about right there. And so now we go over from there. I'm going to say about, like 94 apples. So I'm sorry, 94%. What percentile? About the 94th percentile. So 124 appears to be bigger than like 94% of apples. All right, and then the other main skill is stating the significance of when it's steep and when it's shallow. State the interval that contains the most data points. Where is it most steep? Well, it's most steep in here. I'm going to say just like between 110 and like 120. So most data points is 110 and 120 because it is the most steep. Have to know that about an ogive. Where is it least steep? Well, between 80, I'm going to say between 80 and 110. And then also like between 120 and 140. And 120 and 140 because it is most shallow there. That means there's not a lot of data points. And then lastly, to draw a sketch of a histogram of what this is based on. And so, and if we think about this, so there's our ogive. Remember, wherever it's steep, there's not many points. Wherever it's shallow, there's not many points. Wherever it's steep, there's a lot. So if we did a rough sketch of this, so of what the raw data was that this came from, so I'll just go 80, 90, 100, and 110, and 120, and 130, and 140. Okay, and so if we did a really rough, there's not many points between 80 and 110. So I'm just going to draw just not many. It's going to be really low there relatively. This is just a rough sketch of what's going on. But there's a lot of points between 110 and 120 certainly. So there's a lot of points between 110 and 120. And then it appears to be between, like, not many points, like between 120 and 140. So it'd be really shallow there. So just wherever it's, once again, wherever it's flat, not many points. Wherever it's steep, it's going up, there's a lot of points. So that's it. Thanks for paying attention. I wish you much success with finding locations, percentiles, z-scores, relative cumulative frequency plots. Next time we're going to talk about the normal model.